Lithography is a fascinating process at the heart of modern technology. It's the technique used to create intricate patterns on semiconductor wafers, which are the foundation of microchips. Imagine trying to draw incredibly tiny circuits smaller than the width of a human hair onto a flat surface. That's essentially what lithography does. This process is crucial for making the chips that power our computers, smartphones, and countless other devices. Over the years, lithography has evolved, becoming more precise and efficient, enabling the rapid advancement of electronics. In this video, we'll explore how lithography works, its history, and why it's so important. Lithography actually began as a printing technique in the late 18th century. Invented by Eloi Senefelder, it was originally used to reproduce artwork and text. The word itself comes from the Greek words for stone and writing, since the first lithographs were made using flat stones. Over time, the technique was adapted for industrial uses, eventually finding its way into the world of electronics. Today, the principles of lithography remain the same, transferring patterns onto a surface. But instead of stones and ink, we now use advanced machines and light to create microscopic circuits. Leap from traditional printing to microchip manufacturing is truly remarkable. In the early days, lithography was about reproducing images and text. But as technology advanced, engineers realized the same concept could be used to etch tiny patterns onto silicon wafers. This adaptation allowed for the mass production of microchips, which are now essential in everything from cars to medical devices. The transition required new materials, more precise equipment, and a deep understanding of both chemistry and physics. Today, lithography is a cornerstone of the semiconductor industry, enabling the creation of ever smaller and more powerful chips. One of the most intriguing aspects of modern lithography is the use of light. In semiconductor manufacturing, a process called photolithography uses ultraviolet light to transfer patterns onto a wafer. A special mask known as a photomask contains the desired circuit pattern. When light shines through the mask, it projects the pattern onto a light-sensitive material called photoresist. This step is crucial for defining the tiny features of a microchip. The wavelength of light determines how small the features can be, so advances in light sources have allowed for ever smaller circuits. Photomasks are like stencils for microchips. They contain the intricate patterns that will be transferred onto the wafer. Each layer of a microchip requires its own unique mask, and creating these masks is a highly specialized process. The patterns are designed using advanced computer software and then etched onto a glass plate coated with a thin layer of metal. During photolithography, light passes through the transparent areas of the mask, exposing the photoresist underneath. The precision of the photomask directly affects the quality and performance of the final chip. Photoresist is a special light-sensitive material applied to the surface of a wafer before exposure. When exposed to light through the photomask, the photoresist undergoes a chemical change. Depending on the type of photoresist used, the exposed or unexposed areas become soluble and can be washed away, revealing the underlying wafer. This step is essential for creating the detailed patterns needed for microchips. The development of advanced photoresists has been key to achieving smaller and more complex chip designs. After the photoresist has been exposed and developed, the next step is etching. Etching removes the unprotected parts of the wafer, leaving behind the desired pattern. There are two main types of etching: wet etching, which uses chemicals, and dry etching, which uses plasma. Both methods require precise control to ensure that only the intended areas are removed. Etching is a critical step in defining the features of a microchip, and advances in etching technology have enabled the production of chips with incredibly small and complex structures. Microchips are built up layer by layer, with each layer requiring its own lithography process. After one layer is patterned and etched, additional materials are deposited and the process repeats. This multi-layer construction allows for the creation of complex circuits with millions or even billions of transistors. The alignment of each layer is critical, as even the slightest misalignment can cause defects in the final chip. Modern lithography machines use advanced alignment systems to ensure perfect registration between layers. One of the main goals in lithography is to create smaller and smaller features on microchips. This trend, known as scaling, has driven the rapid increase in computing power over the past decades. As feature sizes shrink, more transistors can fit onto a single chip, making devices faster and more efficient. Achieving smaller features requires advances in every part of the lithography process, from light sources to photoresists to etching techniques. The race to shrink features continues to push the boundaries of science and engineering. Moore's Law, named after Intel co-founder Gordon Moore, predicts that the number of transistors on a chip will double roughly every 2 years. Lithography has played a central role in making this prediction a reality. By enabling the creation of ever smaller features, lithography has allowed chipmakers to pack more transistors into the same space. This has led to exponential growth in computing power and the rapid evolution of technology. However, as features approach the limits of physics, continuing this trend becomes increasingly challenging. As feature sizes have shrunk, traditional optical lithography has begun to reach its physical limits. The wavelength of light used in the process determines how small the features can be. When features become smaller than the wavelength of light, it becomes increasingly difficult to create accurate patterns. This challenge has driven the development of new techniques and technologies, such as extreme ultraviolet EUV lithography, to continue the trend of miniaturization. Extreme ultraviolet EUV lithography is the latest breakthrough in the quest for smaller features. EUV uses light with a much shorter wavelength than traditional methods, allowing for the creation of even tinier patterns. This technology requires entirely new equipment, including powerful light sources and ultra-precise optics. EUV lithography is already being used to manufacture the most advanced microchips, enabling continued progress in computing power and efficiency. Lithography machines, also known as steppers or scanners, are among the most complex pieces of equipment in the world. These machines use advanced optics, precision motion systems, and powerful light sources to transfer patterns onto wafers. Building and maintaining these machines requires expertise in physics, engineering, and computer science. The cost of a single lithography machine can reach hundreds of millions of dollars, reflecting their critical role in chip manufacturing. Optics used in lithography machines are some of the most precise ever made. Lenses and mirrors must be manufactured to exacting standards, with surfaces polished to within a fraction of a wavelength of light. Any imperfection can distort the pattern and ruin the chip. The development of advanced optical materials and manufacturing techniques has been essential for pushing the limits of lithography and enabling the production of ever smaller features. Lithography and other semiconductor manufacturing processes take place in cleanrooms, special environments designed to minimize dust and contaminants. Even a single speck of dust can ruin a microchip, so cleanrooms use advanced filtration systems and strict protocols to keep the air as pure as possible. Workers wear special suits, and equipment is regularly cleaned and maintained. The cleanroom environment is essential for producing high-quality chips with extremely small features. Modern lithography relies heavily on automation. Robots and computer-controlled systems handle wafers, load materials, and monitor every step of the process. Automation ensures consistency, reduces the risk of human error, and allows for the high-speed production required by today's electronics industry. The integration of artificial intelligence and machine learning is further improving the efficiency and precision of lithography processes. A variety of materials are used in the lithography process. Silicon wafers serve as the base for microchips, while photoresists and other chemicals are used to create and develop patterns. Advanced materials such as high-K dielectrics and metal gates are also incorporated to improve chip performance. The choice of materials affects everything from the speed and power consumption of the chip to its durability and cost. Lithography faces numerous challenges as the demand for smaller, faster, and more efficient chips grows. Maintaining precision at the nanoscale is incredibly difficult, and even minor defects can cause major problems. The cost of equipment and materials continues to rise, and the complexity of the process requires constant innovation. Researchers and engineers are working tirelessly to overcome these challenges and keep the industry moving forward. Quality control is a critical part of the lithography process. Even the smallest defect can render a chip useless, so manufacturers use advanced inspection systems to detect and correct problems. Automated optical inspection, electron microscopy, and other techniques are used to examine wafers at every stage. Continuous monitoring and feedback help ensure that only the highest quality chips make it to market. Yield refers to the percentage of usable chips produced from each wafer. High yield is essential for keeping costs down and meeting demand. Lithography plays a major role in determining yield, as defects and misalignments can reduce the number of good chips. Manufacturers constantly refine their processes to improve yield, using data analysis and process optimization to identify and eliminate sources of error. Lithography is one of the most expensive steps in chip manufacturing. The cost of equipment, materials, and cleanroom facilities is enormous. However, the ability to produce millions of chips from a single wafer makes the investment worthwhile. The economics of lithography drive the entire semiconductor industry, influencing everything from research and development to pricing and market competition. Lithography process, like other semiconductor manufacturing steps, has an environmental impact. It uses significant amounts of energy and water, and some chemicals can be hazardous if not handled properly. Manufacturers are working to reduce their environmental footprint by recycling materials, improving energy efficiency, and developing greener processes. Sustainability is becoming an increasingly important consideration in the industry. Lithography is part of a complex global supply chain. The machines, materials, and expertise required are sourced from around the world. Companies in the United States, Europe, and Asia all play vital roles in the industry. Disruptions in the supply chain, such as shortages of materials or geopolitical tensions, can have significant impacts on chip production and availability. Several companies are leaders in the field of lithography. ASML, based in the Netherlands, is the world's largest supplier of lithography machines, particularly for EUV technology. Other major players include Nikon and Canon in Japan, which produce equipment for traditional optical lithography. These companies invest heavily in research and development to stay at the forefront of technology and meet the demands of the semiconductor industry. Continuous research and innovation are essential for the advancement of lithography. Scientists and engineers are constantly developing new materials, techniques, and equipment to push the boundaries of what's possible. Collaboration between industry, academia, and government agencies helps drive progress and ensures that the technology keeps pace with the demands of the digital age. The future of lithography is full of exciting possibilities. Researchers are exploring new approaches, such as nano-imprint lithography and directed self-assembly, to create even smaller and more complex patterns. Advances in materials science, optics, and computing will continue to shape the evolution of lithography. As the demand for faster, smaller, and more efficient chips grows, the industry will keep pushing the limits of what's possible. Though most people never see a lithography machine, its impact is everywhere. The microchips created using lithography power our smartphones, computers, cars, and even household appliances. Without lithography, the modern digital world would not exist. The process enables the creation of devices that are faster, smaller, and more powerful than ever before, transforming the way we live, work, and communicate. Artificial intelligence, AI, relies on powerful microchips, many of which are made possible by advanced lithography. As AI applications become more widespread, the demand for high-performance chips continues to grow. Lithography enables the creation of specialized chips designed for AI tasks, such as neural networks and machine learning. The synergy between lithography and AI is driving rapid progress in both fields. Lithography is also essential in the medical field. Many modern medical devices, from imaging equipment to wearable health monitors, rely on microchips produced using lithography. These chips enable advanced features such as real-time data processing and wireless communication, improving patient care and outcomes. As healthcare technology advances, lithography will continue to play a vital role. Automotive industry is another area where lithography has a major impact. Modern cars are packed with microchips that control everything from engine performance to safety systems and entertainment features. Lithography enables the production of reliable, high-performance chips that meet the demanding requirements of automotive applications. As vehicles become more connected and autonomous, the importance of lithography will only grow. Consumer electronics, from smartphones to smart TVs and gaming consoles, all rely on microchips made with lithography. The demand for more powerful and energy-efficient devices drives continuous innovation in lithography techniques. As new products and features emerge, lithography will remain at the forefront of consumer technology. Internet of Things, IoT, connects billions of devices, from smart thermostats to industrial sensors. Lithography enables the production of tiny, low-power chips that make IoT possible. As the number of connected devices grows, lithography will play an even greater role in shaping the future of technology and connectivity. Data centers are the backbone of the digital world, processing and storing vast amounts of information. Lithography enables the creation of high-performance chips that power servers and networking equipment. As demand for cloud computing and big data grows, advances in lithography will be essential for meeting the needs of data centers. Space exploration and satellite technology rely on advanced microchips made with lithography. These chips must withstand extreme conditions, such as radiation and temperature fluctuations. Lithography enables the production of specialized chips that meet the unique requirements of space missions, supporting everything from communication to scientific research. Security is a growing concern in the digital age, and lithography plays a role here as well. Secure microchips are used in everything from credit cards to passports and encryption devices. Lithography enables the creation of chips with built-in security features, helping to protect sensitive information and prevent fraud. Modern communication networks, including the internet and mobile phones, depend on microchips made with lithography. These chips enable high-speed data transmission, signal processing, and network management. As communication technologies evolve, lithography will continue to be essential for building the infrastructure that connects the world. Education and research institutions use lithography to train the next generation of scientists and engineers. University labs and research centers often have their own lithography equipment for teaching and experimentation. This hands-on experience is vital for developing the skills needed to advance the field and drive future innovation. National security depends on secure and reliable microchips for defense systems, communications, and intelligence. Lithography enables the production of specialized chips for military and government applications. Ensuring the integrity and security of these chips is a top priority, and advances in lithography help meet these critical needs. Scientific research in fields like physics, chemistry, and biology often relies on microchips made with lithography. These chips are used in advanced instruments, sensors, and experimental setups. Lithography enables the creation of custom devices tailored to specific research needs, supporting breakthroughs across a wide range of disciplines. Renewable energy technologies such as solar panels and wind turbines use microchips made with lithography to control and optimize performance. These chips manage everything from power conversion to system monitoring, helping to make renewable energy more efficient and reliable. As the world shifts toward cleaner energy sources, lithography will play a key role in supporting this transition. Wearable devices, such as smartwatches and fitness trackers, rely on tiny energy-efficient chips made with lithography. These chips enable advanced features like heart rate monitoring, GPS tracking, and wireless communication. Lithography makes it possible to pack powerful technology into small, lightweight devices that fit seamlessly into our daily lives. Smart home devices, from thermostats to security cameras, depend on microchips made with lithography. These chips enable features like remote control, automation, and energy management. As smart homes become more common, lithography will continue to enable new capabilities and improve convenience and efficiency. Financial technology, or fintech, relies on secure and reliable microchips for everything from mobile payments to blockchain applications. Lithography enables the production of chips that meet the high standards required for financial transactions, helping to ensure security and trust in digital finance. Entertainment industry, from streaming services to video games, depends on powerful chips made with lithography. These chips enable high-quality graphics, fast processing, and immersive experiences. As entertainment technology evolves, lithography will continue to play a central role in delivering new and exciting content. Lithography is a constantly evolving field, driven by the relentless pursuit of smaller, faster, and more efficient microchips. As new challenges arise, researchers and engineers will continue to innovate, developing new materials, techniques, and equipment. The future of lithography holds endless possibilities, and its impact will be felt in every aspect of our lives, from technology and healthcare to energy and entertainment.